Hi, we present robust iris presentation attack detection fusing 2D and 3D information. This work is done by Zhao Yuanfang, Adam Chaika, and Kevin Boyer from the Computer Vision Research Lab at the University of Notre Dame. There are several contributions of our work, and this is an extension of our previous conference publication at WACV 2019. So the first contribution in our work is that we propose a robust open source fusion-based classifier to combine our 3D photometric stereo-based features with a 2D textural-based features. And this OSPAD fusion does not come from a simple idea. It is actually validated by experiments. Here, we show that the OSPAD fusion emerges from some experiments we conducted on the NDCLD15 dataset. If you observe the joint score distribution of the 2D PAD and 3D PAD, you can see some very interesting patterns, and a very simple fusion rule arises. For samples predicted as contact lenses by OSPAD 2D, that is, for the red dots and very few blue dots lying to the right of the y-axis, we predict them as contact lenses directly. For other samples which lie to the left of the y-axis, we can predict them with OSPAD 3D. This way, we combine the strength of both the 3D classifier and the 2D classifier. We believe that this structure is not a coincidence. It is because 2D and 3D contains complementary information when it comes to presentation attack detection. We also collect a new dataset called ND-IRIS 3D with images of the same irises with and without texture contact lenses of multiple brands and varying near-infrared illuminations. As you can see in the image right here, we show some examples from the dataset. We have two sensors, the LG 4000 and the IRIS-Guard AD100. We also show paired images from two illuminations, left and right, of the contact lenses from three brands: Johnson & Johnson, Ciba Vision, and Bausch & Lomb. The dataset contains 176 irises in total, that is 88 subjects. Each of them is photographed with and without contact lenses. And this results in 6,838 images in total. Thirdly, we conduct the only systematic evaluation of all available open source iris PAD methods known to us. And we test them on the newly collected ND-IRIS 3D dataset. So here, unlike other baselines that compare their performance directly, we actually gather all the codes of the open source methods and then retrain them on the same NDCLD15 dataset subset until convergence. Then we evaluate them on our newly collected dataset. As shown in the table, our OSPAD fusion generalizes much better to the unseen samples, achieving a state-of-the-art performance on the open source iris presentation attack detection methods. It is worth to note that since our OSPAD fusion uses two images, we also give the other algorithms two images and find the best fusion strategy to make their vote. So we explore feature level fusion and score level fusion, and then we report the best they achieve. Lastly, we want to show a very interesting thing that we observed during our experiments. So we conduct some experiments on this newly collected dataset, and then we find that there is a never considered before complication to iris PAD development. That is, there is a non-negligible impact of temporal changes in the contact lens patterns introduced by manufacturers. And the proposed OSPAD fusion is robust against these changes, while most of the previous methods fail significantly at this task. So on the left here, we can see some image samples. The top row is the Ciba Vision contact lens, bottom row is Johnson & Johnson, and the first column was their patterns in 2012, and the second column is their patterns in 2019. It is interesting that the manufacturers changed their patterns, but they didn't change the name of the contact lens. This might lead to some inefficient training if some methods are trained on the 2012 data and tested directly on the 2019 data. And on the right-hand side, we show quantitatively the performance of our method. On the top is like we trained the method on real and contact irises with patterns from 2012. And we see that all the methods perform really well. And our OSPAD fusion is actually not the best performing one. It is actually the OSPAD 2D, which is very sensitive to the textural changes. And then we take the pre-trained model and test it on the data with contact lens patterns from 2019. Here we see that all the methods dropped their accuracy by nearly 20%, but OSPAD fusion is still able to maintain more than 90% of its accuracy. We believe that it is the 2D and 3D features where 2D is more sensitive to textural patterns and 3D is more sensitive to the shape features, and their complementary nature make our OSPAD fusion more robust. We also showed our generalization to different types of contact lens patterns. So here, the contact regular means that these type of contact lens has a grid-like texture patterns, and contact irregular are the contact lenses without a grid-like texture pattern, as shown in the images here. So if we train on real and contact regular types of contact and test them on a subject disjoint test set of real and irregular patterned lenses, we show that OSPAD fusion achieves the best result. And similarly, it is also the case when we switch the training and test set. It is interesting that OSPAD 2D actually fails pretty hard because it is sensitive to textural patterns and there is a complete change in textural patterns. But OSPAD fusion is still able to combine the useful information given by the 2D PAD and then push the limit of the 3D PAD's performance. So that's it for our paper. If you are interested in learning more about the details, you can check out our paper online, and we also have the codes available on GitHub. If you have any questions, feel free to email us. Thank you so much.